All right, welcome to our first online recorded lecture that I'm going to be posting for our 1211 course here the rest of this semester. For just some kind of quick things before I even get into the topics, if you have general feedback that you want to provide as far as kind of like what way of working problems, that I'm going to do a couple different ways throughout this presentation. If there's a way that you prefer or that people seem to like, please try to give me feedback either through the YouTube link in the comment section or preferably probably just by email is maybe better. And that way I can try to adapt the future videos to hopefully kind of fit what the majority of people seem to like better. And I apologize in advance. There will probably be a little bit of learning curve here with me, kind of some of the interactions. Hopefully it'll go relatively smoothly as far as kind of showing ways to use a kind of a whiteboard here while recording this lecture that you'll see as we get to it. Now, in terms of topics, what I want to talk about today is going to be the second half of Chapter 5. So for my lecture section, only the first couple slides. This is probably review. If you're in one of the other lectures, like Dr. Herbert or Mr. Kruger or some others, you might have already talked about some of these topics. That's fine. So hopefully be a nice review point to kind of get you started back into everything here with this next week. And so as a starting point, we're going to talk about calorimetry, and then we'll work our way into talking about what are some different ways to calculate changes in enthalpy for reactions. And so starting out with calorimetry, this is really what you were probably doing in lab the last week before we all left. And that's really studying where energy is being transferred between like hot and cold objects. So it's the study of heat flow. So in this process, that means if we have energy flowing via heat from hot to cold objects, that means things are changing temperature. So there's always going to be a change in temperature involved. So pretty much any word problem, if you see it in talking about heat and you see it talking about a temperature change of something, pretty much know it's a calorimetry example of some kind. Like there's really no other way around it. And we'll talk here about a couple things about what that's going to mean in terms of setting up our calculations as we start seeing our first few examples. When we also talk about calorimetry, there's two main different kind of experimental types. This is probably less important to how we solve problems and more just kind of just general awareness about how people talk about calorimetry. The majority of calorimetry you probably encounter is going to be what we call constant pressure calorimetry. And so like when we did our coffee cup experiments in lab, those cups were just open to the air. And since the normal air is at a constant atmospheric pressure, we consider that a constant pressure situation. And the reason that's important is at constant pressure, our heat Q is equal to the change in enthalpy for a particular process or a reaction. And so if we're not at constant pressure, generally the other type of calorimetry is going to be a constant volume situation. And really the only time you're probably going to see this is with something called a bomb calorimeter. And I will look at an example of this, and what we'll really see is that setup and calculation-wise, almost nothing changes. The only thing that really changes is usually what we're looking for, whether it's delta E or delta H. And so for constant volume, Q is actually equal to delta E, not just delta H. The reason for that is if we're at constant volume, if we think about delta E to review kind of the early parts of Chapter 5, delta E is equal to Q plus W, right? Heat plus work, but work is pressure times a change in volume. But if we're at a constant volume situation, that means the change in volume is 0, so work is just 0, and delta E is actually just Q for constant volume. That's where that equation is going to come from. All right, now, in terms of working problems, like I said, probably not really going to matter too much which of these it is. The type of calorimetry really matters more what you're probably finding for that particular reaction. Our first example, though, isn't really going to involve a reaction just yet. This is actually very similar to what you were doing in lab. It's often called drop calorimetry, but it is just a kind of a basic calorimetry example. And again, one of the biggest things to note right away, we have different temperatures involved. So temperature changes, any problems with these temperature changes, probably going to be calorimetry based to some degree for everything that we're seeing in this chapter. So how do we go about solving a problem like this? We have a 50-gram piece of metal at 225 degrees, dropped into 125 milliliters of water at 25, and we're told that the temperature of the entire solution, the metal and the water, at the end of everything is 38 degrees, is a final temperature for all of it. And it wants us to calculate the heat that the water is gaining in this process, the heat that the metal is losing, and then the specific heat capacity of the metal. And really, these are kind of the steps that your lab also has you walk through for a lot of the things that you were doing back before break. And really, to get to this last part, we actually kind of have to do these first two, whether we're asked for them or not. So it makes sense to let's just do kind of all three of these and kind of walk through that process. But before we do, there are a couple things that we probably want to be aware of. Right? One is that we're going to need a specific heat capacity for water or in this case, what we're going to use for our solution. And that's that water has a specific heat capacity of 4.18 joules per gram degree Celsius. And the units here are really important, mainly because the biggest mistakes I see in this chapter always deal with either units or signs, like positive or negative. And so when we look at our units here, we see joules per gram degree Celsius. If we talk about heat, heat usually has units of just joules. So that means any equation, if there's grams in this constant, our equation's also going to have a mass somewhere in that equation to help cancel out these grams. That's something to kind of just be aware of. And we'll see through some of the examples that we have coming up where that can kind of be relevant and why you have to pay attention to those units as you set up your equations for things. And the other part of this, if I have grams right here, if I'm looking at water, I don't have grams, I actually have 125 milliliters. But if we think about water, water is probably the only substance that we'd ever expect you to know its density. And that's because its density is just 1 gram per milliliter. And so really 125 milliliters of water, this is just going to be 125 grams that we can then use to find the heat that our water is going to gain. Right? Because the heat that our water is going to be gaining, I'm going to show kind of on the next slide here. To find the heat that our water is gaining, we can use Q equals mc delta T for an equation. We have the mass of the water I just described. We know it's 125 grams because its density is 1. We have the specific heat capacity to C sub S that they gave us as a constant on the previous slide. And then for the delta T, I'll go back real quick for just a second. The only thing with delta T to be careful of is the order does matter. It's always final minus initial. The final temperature is 38 degrees, everything is ending at. And for water, its initial temperature was 25. So if we're putting all of our pieces in for our numbers, we have 125 grams for the mass, 4.18 joules per gram degree Celsius for the specific heat capacity, and for the delta T, it's 38 minus 25. That's our final minus our initial. That gives us a total of about 6,790 joules, or 6.79 kilojoules. The unit you choose to use there doesn't matter too much. Probably actually is maybe better to leave it in joules in this case, although a lot of the times when we're asked for heat or for just energy things in general for these types of problems, especially for reactions, it'll often be like in kilojoules or kilojoules per mole for some of those calculations. Now, the second part that this problem wanted us to find, this is our heat gained by the water. And again, this is positive because the heat for the water is being gained, right? Temperature's going up. The second part, it asks us to find the heat that's lost by the metal. Well, in order to find this part, we can't really use a Q equals mc delta T equation because we don't have the specific heat capacity of our metal, right? So instead, we have to think about what's really going on in this process. Well, if the water has gained all this heat, where did that heat have to come from? Well, the only thing that lost heat is going to be the metal because its temperature did go down. So really, we're going to see that all of that heat that the water gained had to have been heat that the metal lost. And so what that means is that the numbers for their heats should be the same, but for the metal, it should just be negative instead. And in a perfect world, this probably isn't 100% true. You'll probably see that some heat is also not just lost to the water, but maybe the container and the air around the water. And that can be accounted for something called a calorimeter constant, and you actually looked at that a little bit in lab. For the most part, in lecture, I don't know if you'll actually have to deal with that too much. We're going to kind of, for the examples we're going to see here today, kind of just assume that anything that's losing heat, all the heat it loses is going to be gained by whatever else is gaining the heat. We're not really going to take the loss to surroundings into account, mainly because it's usually a very small amount, especially with the numbers that we're going to be working with for most of these examples. But it is important. This Q lost equals negative Q gained. This relationship shows up pretty much for all calorimetry problems. And when you forget about it, your signs for things can start to get a little strange. And so that's why I said that a lot of the most commonly missed things I see in this chapter as a whole are mistakes with signs or mistakes with units. So really try to pay close attention to those two things in all the calculations that you do for all of this chapter. Now, the last part of this problem, they wanted us to find the specific heat capacity of our metal. And so for that, we can go back to using our Q equals mc delta T equation. And now we're just going to rearrange it for C and find that specific heat capacity. So rearranging it for C, right? If I divide the mass and the delta T over, so C should be Q over m delta T. So I put this back in joules here just so our specific heat has joules in its units. That's kind of the more common way it's usually shown. So negative 6,790 joules for our Q. The mass of the metal from our original part of the problem was 50 grams. And then the delta T, this order again is important, right? The final temperature was 38. That's why it's 38 first minus 225. That means this is going to be a big negative number, but that's actually important right? Because if this is not a big negative number, we're not going to cancel out the negative sign from the Q, and we won't get a positive value for C. And something that's important is all specific heat capacities are always positive values. Remember, kind of its general definition is it's the energy it takes to raise the temperature of something by 1 degree. So you're never going to have a negative amount of energy involved in raising the temperature of something. So C should always be positive. That's why our Q that was negative, our delta T should also be negative if the Q is negative. That you kind of always will see that relationship, right? Mass is always positive as well. So if delta T is negative, Q is negative. If delta T is positive, Q is positive. That's kind of the trends you should always see for things. Our end result here when we calculate those, we get our specific heat capacity is about 0.726 joules per gram degree Celsius. And just some general things aside from our specific heat always being positive, the numbers on it usually aren't going to be very large. Water specific heat of 4.18, that's actually pretty big compared to a lot of other things. Most metals are going to be less than 1. Some of them might be significantly less than 1. And the smaller that specific heat, the easier it is for those things to heat up. And remember, like metals get really hot really quick, right? When you heat them up. The reason they do that is their specific heats are small. It doesn't take a lot of energy for them to warm up. Whereas water, if we have to boil water for any of our experiments in lab, remember it takes forever a lot of times for that water to start boiling because water has a high specific heat. It's hard to get all of that water to heat up. And I just gave some kind of references there and what to expect kind of for numerical answers on things when you have to find those values. All right, so let's take a look at a couple other calorimetry examples, but we're going to take a look at now ones that have reactions involved. And so for this, I'm going to actually kind of display this in a slightly different way as well. So let me know which of these kind of display methods you prefer. And for this particular one, I'm calling it kind of a whiteboard example because what I'm going to do here is I'm actually going to work the problem basically on my iPad and kind of write things by hand, how I would set things up and solve it as if I was like writing it on a board in the class. And that way I can also leave the problem just shown the whole time here for you guys to kind of reference as we're going through it. And so if you prefer this method, please let me know and I'll kind of work problems in the future kind of this way rather than kind of in the slides like the last example. And most of the ones we'll probably do the rest of this time. I would like to try this method, if nothing else for me, just to kind of get used to as well. And I know it'll also hopefully help me kind of slow down a little bit and kind of make sure I point out all the things I want to as I solve them. So for the example, we have a neutralization reaction that's being described to us that has 0.013 moles of HCl and 0.013 moles of sodium hydroxide that are reacting. And it takes place under constant pressure. Notice we're looking for delta H. We said at constant pressure, Q and delta H are equal. So that's kind of the relationship we see here. And we're told that our solution has a total mass of 29.4 grams and a specific heat capacity of 4.05 joules per gram degree Celsius. If the reaction causes the solution to raise in temperature from 22.4 to 28.5 degrees Celsius, calculate delta H for the neutralization reaction in units of kilojoules per mole. So a lot of different pieces here. We do notice there's only one temperature change this time, right? So that is going to be kind of important in terms of how we kind of put everything together to get started. A couple things though right off the bat. So we're looking for delta H in general. Well, in general, delta H, right? We said at constant pressure, delta H is just equal to Q. And we'll say Q of our reaction in particular. We'll see why I'm going to want to be specific here in just a moment. And even more particular, if our units need to be kilojoules per mole, the other piece we're going to see here is that when we go to calculate our delta H, Q is typically just in units of joules or kilojoules if we put it in kilojoules. So to get that moles part, we have to divide the Q of our reaction by the moles of our limiting reagent. Right? So there's delta H is Q of our reaction over moles of our limiting reagent. That's kind of the last step that we want to be able to put together for this problem. And that anytime you see you're looking for delta H or delta E and it's kilojoules per mole, you're going to have kind of this divided by moles of limiting reagent component added to that, Q equals delta H or Q equals delta E kind of equation. Now, to solve this, we have the moles of our reactants, right? An HCl reacting with NaOH should just be a one-to-one reaction, right? If I wrote it out, we'd have HCl plus NaOH. Hopefully, it's a reaction you can kind of identify from a couple chapters ago. It's going to be making water, and sodium chloride. And that is already balanced, right? Everything's 1 to 1 to 1. So really, as we look at our two reactants, if we have the same amount of each of them, and it's a 1 to 1 reaction, well, 0.013 moles, that is the moles of our limiting reagent in this case. So we have the moles of limiting we need here. What we need to find is Q of our reaction. Well, if we look at the information they give us, we have a mass, we have a specific heat, and we have a temperature change. But the problem is those aren't for our reaction, those are for our whole solution that everything's taking place in, right? And so we can find Q of our solution by doing our normal MC delta T equation. And I'll try to clean up my handwriting as best I can here as we go. So we have Q of our solution is equal to MC delta T. And we have, like I said, we have the mass, we have the specific heat, we can calculate that temperature change. So we can actually go ahead and find Q of our solution by just plugging in our numbers here. So 29.4 grams for the mass, 4.05 joules over grams degrees Celsius for the specific heat. And then our delta T part of the equation, right, the delta T here is going to be 28.5 as the final, minus 22.4 as the initial. So 6.1 degrees Celsius for the delta T. And hopefully that's legible enough for everyone to kind of see as we're going through it. Now, if we multiply all of those pieces together, so multiplying all of this out, we can find our Q. Comes out to about 726 joules. Or if we want to round it, since we only have 6.1 degrees Celsius, only technically really has two significant digits, we could say this is 730 joules is going to be Q of our solution. Now, what we need, though, to find our delta H of our reaction, we need Q of our reaction, right? So this is the last part where, like, the fact that we're talking about calorimetry, and we have to understand kind of where all of our energy is going. For our solution to have gained heat, something has to lose that heat, and that something that loses the heat has to be, in this case, then our reaction. So Q of our reaction should be equal to Q of our solution, but they should be opposite in sign, right? That's really, like we said, like the Q lost equals negative Q gained, or however you want to put the negative sign, whichever side you want, doesn't really matter. But the two should be equal, just opposite in sign. So that means Q of our reaction should actually be equal to negative 730 joules. And now we can go through and find our last part of this and find delta H, right? We said before that delta H of our reaction is Q of our reaction divided by moles of our limiting reagent. So if I go back down, we found Q of our solution, which we can use this relationship to find Q of our reaction. So now to find the last bit of this for delta H of our reaction, it's going to be equal to our Q of our reaction, negative 730 joules, divided by the moles of our limiting reagent, which was 0.013 moles. Clean that up just a little bit. And so if we calculate this, we're going to get something that's about 56,000, I think it's like 150 roughly joules per mole for our units. And again, sig fig wise, if we rounded to two significant digits earlier, we can round to two significant digits again. And I've forgotten one last part here. It should be negative 56,150. Converting this to kilojoules per mole, which is the units we want that we're asked for, we'd get negative 56 kilojoules per mole as our final answer. Right, so those would be kind of our steps or our thought process going through this. And that's going to be pretty typical. Most calorimetry problems, we'll work one more of these as well, are going to involve looking at this kind of relationship of what's gaining heat and what's losing it. In this case, we have a solution that's gaining heat, but if a solution's gaining heat, the only way that happens is for a reaction that's taking place in the solution, the reaction has to be giving off that heat. And that's why we have a negative delta H over here for our final answer. And it is pretty typical for delta H's and delta E's of reactions to be very large values. Like if it's in units of joules per mole, it's probably going to be thousands or maybe even hundreds of thousands. If it's in kilojoules per mole, usually anywhere from here we see 56. We might even see it up to like a few thousand kilojoules per mole. That's possible. Like hundreds of kilojoules per mole is common for a lot of these different reactions. All right, so let's take a look at one more example. I think I'm going to go through this a similar process. So I'm going to take the whiteboard over here and just kind of scroll it down so we can take a look at a new example. So this next one, we have 0.55 grams of something called anthracene, and they give us this formula C14H10 is combusted in a bomb calorimeter, which as soon as we see that word like bomb calorimeter, right? This is what we said before, bomb calorimeter basically means that we're a constant volume situation. But the only thing that really matters for is the fact that that last example we were looking for delta H. Notice in this example we're looking for delta E. The rest of this problem is still very similar to what we just did. So in terms of since we are at constant volume, that means that delta E of our reaction is going to be equal to Q of our reaction. And again, since we want kilojoules per mole as final units, it'll be Q of our reaction divided by the moles of our limiting reagent, which in this problem, they only give us one reactant and it's being combusted. So remember, combustion reactions are reactant plus oxygen. You can probably assume that oxygen's in excess here. And so this is our limiting reagent. We just are going to need that in moles instead of grams, which we can get to that part at the very end. So we can find moles of limiting reagent by converting to grams. So we need to find, again, Q of our reaction. And so if we look again at the rest of our information, we have our calorimeter when this sample is combusted. The calorimeter increases in temperature from 24.3 to 35.8 degrees Celsius. And they tell us the heat capacity of the bomb calorimeter is 1.57 kilojoules per degree Celsius. So we have a change in temperature. So we can probably have an equation for Q. But unlike our last example where we used Q equals MC delta T, this equation is actually just going to be plain, clean this up, is going to be just C delta T. There's no M involved. And if we want to know why that is, the answer is here in our units. Right? Like I said before, sign conventions and units, it's where the mistakes come from. There's no mass or moles in this constant. So there's not going to be any mass or moles in our equation for Q. It's just going to be Q equals C delta T. And that's it. And so we have the pieces for that. Now, the other part, though, is which Q is this? This isn't Q of our reaction because it's not our reaction that's changing temperature. It's the calorimeter. So what I'm really finding here is Q of, call this our calorimeter, Q cal. So Q of our calorimeter is C delta T. If I put my pieces in, C we said was 1.57 kilojoules per degree Celsius times my temperature change, right? Final minus initial, so 35.8 minus 24.3. So that's going to be, let's see, what does that come out to? About 11.5 degrees for the temperature change difference. And if we multiply that by the 1.57 kilojoules, I think we get something in the area of about 18.1 kilojoules. So we get about 18.1 kilojoules. That's the Q of our calorimeter. But again, if we want delta E of our reaction, that means we need Q for the reaction, not the calorimeter. Well, for the calorimeter to heat up, kind of like our last example, that means our reaction has to be giving off the heat that the calorimeter is absorbing. So that means that Q of our calorimeter should be equal to Q of our reaction. But again, these two things are opposite in sign. Right, and so in this case, Q of our reaction is then going to be negative 18.1 kilojoules. And now if we want to solve this problem, we want delta E. We said a second ago that delta E is Q of our reaction over moles of our limiting reagent. Now we can set up an equation for delta E from that then. So our delta E is going to be negative 18.1 kilojoules divided by the moles of our limiting reagent. So this last part, we have 4.55 grams of anthracene, the C14H10. So we do need to convert those grams to moles. So I'm going to show this here on 0. If I can write a little clearer. 0.455 grams of C14H10 divided by, really dividing by its molar mass. Or actually, I can show this probably a little bit better. I'll do this kind of the way I normally would, just kind of almost show it dimensional analysis wise. All right, we want to get to moles. Dividing by grams. So we need its molar mass. Right, if we find the molar mass of anthracene, I think it's probably, what is that? Probably about 178, roughly. And now we have all the pieces that we need, this whole bottom part, right? This chunk right here. This will give us the moles of our anthracene that are being combusted. That's the energy change that happens when we combust that many moles. And so now if we basically divide and multiply all of this out, delta E of our reaction ends up coming out to about negative 7,070 kilojoules per mole for our final units. And that is a really big delta E for it to be that large in kilojoules per mole, but that can still happen. And if you actually look up what's the delta E or delta H of a reaction for the combustion of anthracene, it is pretty close to that value. It's a very large number. There's a lot of hydrocarbons that give off very large amounts of energy when you combust them. That's why they're used for things like gasoline and stuff like that. All right. So I think that's going to be kind of that covers probably the majority of the different calorimetry problems that we're going to see. We saw these last two, you were looking for like delta H and delta E because we had a constant pressure and a constant volume situation. But really, the setup of the problems and solving them are more or less the same. It's just what are you looking for at the end? If it's a bomb calorimeter, that basically means you're probably looking for delta E because it's a constant volume situation. If it's not a bomb calorimeter, if it's constant pressure, like our previous example where we had basically it's kind of almost like what we call coffee cup calorimetry. In that case, we're looking for delta H. Those are the only real differences that we see there. All right. So I'm going to move on kind of to the next few things here. Some's going to be a little bit terminology, but we're going to lead into really focusing on enthalpy for reactions, because that's really when we talk about delta H in general. Let me get this to respond. Talking about delta H for chemical reactions, it's going to be pretty informative in terms of like what goes on from an energy perspective when those reactions occur. And so we have some terminology to describe reactions that either give off or absorb heat when they take place, in endothermic and exothermic. And what these are, if something is endothermic, all that term really means is that that particular reaction is absorbing heat from the surroundings as it happens. And so another way that I often like to think about endothermic reactions is that heat is kind of like an additional reactant. Kind of have to add heat to the reaction for it to happen appropriately. And likewise then for exothermic reactions, that means that heat's being released into the surroundings. So you can often think of heat as kind of like an additional product in that case. Now, what this also means, if you think about the signs, for something to be endothermic, that means delta H is positive or bigger than 0. If something is exothermic, that simply means delta H is negative for that process, less than 0. And so that's probably another like maybe more formal way of thinking about numerically like whether a reaction is endothermic or exothermic. And so looking at kind of some relationships then, here we see a reaction. This is actually a thermite reaction if you're not familiar with it. If we have aluminum metal reacting with iron oxide to make iron metal and aluminum oxide, this is an extremely exothermic reaction. And it's exothermic because we have a big negative delta H value for that reaction. Now, an interesting thing that can happen when you reverse a chemical reaction, you actually end up basically flipping the sign of the delta H for that reaction, right? The second reaction that we see down here at the bottom, all we've done is reverse our reactants and products in this case, and the end result of what we're looking at is that our delta H just switched sign. The number didn't change, just the sign did. That's going to be important for some of the things we're going to be looking at here in just a second in terms of different ways that we can calculate delta H for a chemical reaction, because that is kind of a useful piece of information and something that you will probably have to calculate on future tests, quizzes, and probably in the final exam, I can almost guarantee as well. And so we're going to take a look at kind of what are some of the other things that we want to be aware of so that we can use some of these different methods to find delta H for whole reactions. So first thing I'm going to look at is as we kind of just manipulate reactions in different ways. So if we're told, we're given these two reactions, so this top reaction A plus 2B going to C, the delta H of this reaction we call delta H1. And then we also have a secondary reaction C going to 2D, it's delta H, and we're going to call it delta H2. If I want to know what is the delta H for the reaction of 2A plus 4B making 2C, which is really just this top reaction all multiplied by 2, well, to get the new delta H is just 2 times whatever that original delta H was, and that's it. So if you multiply all of your coefficients by the same constant, you multiply the delta H by that constant as well. Hopefully that kind of makes some intuitive sense for doing that. If you reverse the reaction, this is what we said basically on the last slide. All you do by reversing the reaction is switch the sign. The number stays the same in that case. And then the other piece that we're going to look at here, if we want to combine reactions. So I want to know what's the delta H for A plus 2B going to 2D. Well, if I add these two reactions together, right, this reaction plus this reaction, the C's on the opposite sides will cancel, and adding these two reactions together really gives A plus 2B makes 2D, which is what I have down here. And the delta H for the two reactions that we add together, the new delta H for the overall reaction is actually just the sum of the delta H's for the things you add together. And the reason we kind of show this or go over this, this is a really prevalent kind of thing that's going to show up in what we call Hess's law, which is the first way we're going to look at for finding delta H for a reaction. So to kind of show what Hess's law is really trying to demonstrate, and we'll look at kind of a full example here in a second. If we want to know basically the delta H of some new reaction that we haven't experimentally done, if we know other similar reactions that we can basically add together in some way to get a new reaction that we're interested in, then we can find the delta, or at least approximate the delta H of our new reaction based on the delta H's of the reactions we already knew. So we actually have ways to kind of almost save us time experimentally for finding delta H for reactions if we can kind of have other kind of pre-existing information that we know how to use. So I think that the best thing to do here is to try and look at some examples. And so again, I said I'm going to do this kind of like a whiteboard type style on this one so I can write this out. These problems, they look really confusing, I think, the first couple of times you go to do them. And then honestly, after that, they start to get pretty easy in most cases. So how problems like this are going to work. We're asked to use Hess's law to determine delta H for this overall reaction, given the delta H's for these three different reactions at the bottom. So how to approach problems like this. Oops, I apologize for that. How we're actually going to go about doing this is that we're going to be taking each one of these reactions and just trying to figure out what do we have to do to each individual reaction that we know about for the delta H before we try to add all, really our end goal is trying to add all these reactions together to get the overall one. But the problem is if I take these three reactions as they're written right now and add them up, I'm not going to get the reaction up here that I want. So the best thing I think to usually do is look one reaction at a time and try to find something in each reaction that only shows up in that reaction and is in your overall reaction. So what I mean by that, for this first reaction, we have CO plus H2 making carbon solid plus water. Well, water is in our overall reaction on the reactant side. Carbon also is in our overall reaction on the reactant side. But water also shows up in our second reaction. So really the best thing to look at here is probably the carbon solid. Because if I take the carbon solid, I know I want it on the reactant side of my reaction. And this carbon solid isn't anywhere in my second or third reaction, right, or any of the remaining reactions. So that means the only way for me to add these three reactions together and end up with two carbon solids on the reactant side is if I take this first reaction that they've given me and I rewrite it, but I'm going to have to reverse it so that the carbon's on the other side. And I'm going to have to multiply all of it by 2 so that I have 2 carbons. And so if I do that, this top reaction, if I rewrite it, and this one I'm going to show kind of on the whiteboard here on the side, if I rewrite this, I'm going to end up with 2 carbon solid plus, this will be, if I'm multiplying everything by 2, 2H2O as a gas. And that's now going to be going to 2CO as a gas and H2, 2H2 as a gas. Right, so everything in that reaction got multiplied by 2, and everything in that reaction got reversed, right? So it switched sides. So what that does to the delta H then for this reaction is that the delta H, instead of being, I'm going to write this kind of up here a little bit because I ran myself out of room already. The delta H, instead of being negative 131 kilojoules, this delta H for this version, the reversed and multiplied by 2 version, if I reverse the reaction, it's going to become positive. And if I multiply it all by 2, I need to multiply this by 2. So instead of negative 131, it's instead going to be positive 262 kilojoules. Right, that's what I've changed it to. Now I'm going to take a similar approach to this second reaction, and I'm going to look for what reactant or product kind of matches up and only is in that second reaction. And if I look up here, like CO is in all of them, H2O is in all of them, but CO2 is only in this middle reaction, right? There's no CO2 in the first or third reaction. So all of the CO2 that I need on the product side of the overall reaction has to come from the second reaction. Well, here's CO2. It's on the correct side of the reaction. It's already a product. And there's one of them. The coefficients kind of already match, which means the second reaction, I don't have to do anything to it. I can leave it exactly how it is. So that means I'm going to have CO as a gas plus H2O as a gas is going to CO2 as a gas and H2 as a gas. And the delta H for this one, since we didn't change anything, it stays exactly the same. Right? So delta H still going to be just that negative 41 kilojoules. So that's starting to get a little tight. I'll rewrite these numbers for the delta H's at the bottom as I write it all out. Third reaction, going to look for kind of the same thing. We want to find like what's in this bottom reaction, doesn't show up anywhere else. Well, CO's in the other reactions, H2 also in the other reactions. Methane, CH4. Methane needs to be on the product side in the overall reaction. It's not in either of the first two, so that means this methane is already on the correct side. I need one of them. I already have one of them. So that means this last reaction also needs to stay exactly the way it is currently. I don't need to change anything to it, and that should give me the correct amount of methane for my product. So if I leave that reaction alone as well, I'll again have CO as a gas, plus this time 3H2 as a gas is going to CH4 as a gas, and again, this one's H2O. Oops. Clean that up a little bit. Try to anyway. Hopefully I will get a little bit better at writing on this as kind of the semester goes along as well, if people like me doing problems in this version. And so, since I didn't change anything for this last reaction, the delta H here for this last reaction is going to be negative 206 kilojoules still. Nothing's going to change. And what I want to kind of now do at the end of all of this, I have all three of the reactions that I've now written over here, hopefully all set up so that if I take and I just basically add them all together, what I should end up with is the reaction I was interested in originally. So by looking at these two reactions, I notice that I have two COs on the top right over here on the product side, but I also have two COs over here on the reactant side. That means those things are going to cancel out, right? So those are gone from my overall reaction. I also notice I have 2H2 and another H2 for a total of 3H2 on the product side. And the last one has 3H2 on the reactant side. So all of those are also going to cancel out when I add these all together. And I have one last thing that I have one last thing that actually cancels. I have 2H2 here, 2H2O, another H2 on the reactant side, but one H2O on the product side. So one H2O on each side also cancels. And now the only things that are left are 2 carbon as a solid, plus 2 waters as a gas, going to CO2 as a gas, and CH4 as a gas. And if I want to find my new delta H for that reaction, all I should have to do is add all of these other delta H's. Right? And so I have positive 262 plus a negative 41 plus a negative 206. And if I add all of those together, I end up getting something that looks like it's about positive, is that positive 15 kilojoules at the end of all of this. So 15 kilojoules, and it should be the final answer. For that overall reaction. So I promise the first time through an example like this, it looks really weird, but they really aren't that bad. You're trying to find a way to take all the reactions they give you and just kind of organize them so you can add them all together to get the actual reaction they ask you about. That's how Hess's law as a whole typically works for examples. And I think the most systematic way of usually doing it, try to pick out one reactant in each individual reaction. It doesn't have to be even a reactant, just a reactant or product. One compound that only shows up in that one reaction. Like the first reaction, it's the only one of the 3 we were given that had carbon as a solid, which we knew we needed as a reactant, and we knew we needed 2 of them. That's why this first reaction was reversed and multiplied by 2. In the second reaction, CO2 shows up in it and doesn't show up in the first or third reaction, but we need CO2 as a product. We need 1 CO2. Well, we already had 1 CO2 here. That's why this reaction didn't change. For the third reaction, that compound was methane, CH4. We needed methane as a product in one of them. We already had it on the product side with one of them. Methane doesn't show up in the other reaction, so we knew the last reaction also wouldn't change. And then we could, once we kind of manipulated each equation the way it needed to be manipulated, add them all together. Everything should cancel out correctly if you organize it all right. And then you can go through and add the delta H's of your new reactions after you've kind of changed them appropriately to find the delta H of your whole reaction. And like I said, it sounds kind of convoluted and maybe looks really tricky at first. After you do about 2 or 3 examples, they actually get pretty easy because it's kind of the same general steps really each time. All right. So I don't want this to take too much longer because I don't want these lectures to all be like 1.5 to 2 hours plus. I think that's kind of outrageous. We only normally have 50-minute classes. But I do have one last kind of set of things I want to talk about, kind of a second way of calculating delta H for a reaction. And so that other way that we're going to be taking a look at is going to involve something called standard states. And so I'll have a little bit of terminology pieces here, and then I'll show the other way of actually calculating a change in enthalpy for a reaction. So thermodynamic standard states. First off, this is kind of a general terminology piece. So for something to be a thermodynamic standard state for like solids, liquids, and gases, it basically means that we're talking about the most stable form of that compound when it's at the conditions of being at 1 atmosphere of pressure and a specific temperature that is generally always 25 degrees Celsius. One other thing I do want to point out, standard states for elements. This is something that I think almost all faculty usually try to get our students to just know. And so I'm adding this kind of in here to this slide. These elements that I have listed here are always diatomic, always. And I'll show a picture of a periodic table, I think, here in a second that will kind of help re-emphasize this and show where they are. When we see the periodic table, it's actually not so bad because really H2 is the only oddball, and the rest of these make kind of like an inverted L in the upper right corner of like the periodic table. And so we'll see that again kind of in a second. But hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, iodine, it's like all our halogens basically, and then like hydrogen, nitrogen, and oxygen. Like all of these are what we call diatomics. And what that means is if you find those elements in nature, they're going to exist as diatomic molecules. Like you're never going to find oxygen as a plain oxygen atom. Like if you find elemental oxygen, it's always O2. Same thing for hydrogen or for chlorine or iodine or any of the other ones on that list. Now, standard states, one other thing for solutions, This matters not really much for 1211. It'll pop up probably more at the end of 1212. But for a solution to technically be at a state, what we call a standard state, it's going to have a concentration of 1 molar. Like I said, probably not going to matter too much really for this semester. Probably the biggest things, thermodynamic standard state, 1 atmosphere of pressure, 25 degrees Celsius, and we want to recognize what things are diatomic, because we're going to see this pop up again with something called the Born-Haber cycle in particular a little bit later this semester. Now, standard changes in enthalpy. Like everything we've talked about in this chapter so far, like we were talking about, change in enthalpy being delta H. If we're under standard conditions, so basically if these stipulations are met for like 1 atmosphere, 25 degrees, you'll often see this little degree symbol after the delta H. So like delta H naught, this is kind of how we often refer to that, delta H naught. Delta H naught basically means it's the delta H at that exact temperature and pressure for standard conditions. So 1 atmosphere and 25 degrees. Now, standard states in general, we don't have the luxury, since you guys aren't in our classrooms anymore. The periodic tables in our classrooms are really nice because if you remember right, there was colors to all of the elements, and it was actually color-coded by what the physical state of things were. So you don't kind of have that luxury probably of having that specific periodic table near you. So I just wanted to kind of highlight what I mentioned before. We do expect you to know which elements are diatomic. Those are, like I said before, hydrogen, and then kind of this inverted L in the upper right corner. It's like nitrogen, oxygen, and fluorine, and then down the halogens, like chlorine, bromine, and iodine. So these 6 over here in this upside down L, and then the hydrogen over here. Those are all of our, we call diatomic elements. Everything else in the periodic table, the vast majority of them, like all of our metals, their standard state is just like for titanium, it would just be titanium metal. That's it. Like so Ti as a solid. Like same thing, iron solid. That would be its standard state. There are a couple other ones that can be weird, like phosphorus, sulfur. If there are other weird ones, like carbon fits that as well, we would actually tell you what their standard states are. Like in terms of like if they're not just like that element as a solid, or if they're one of our diatomics that I just kind of introduced. Now, why is this kind of important? Because the other way we find delta H of reactions, like whole reactions, is using something called a standard heat of formation. So what a standard heat of formation is, symbol-wise, you're typically going to see it as delta HF naught. And it's the enthalpy change for making exactly 1 mole of a substance in its standard state forms, like whatever that form is, like for a compound, like if it's water, for instance, water is normally a liquid under standard conditions. So like this delta HF naught for water would be making 1 mole of water as a liquid from its constituent elements in their standard states, which would mean for water, that would be like H2 as a gas and O2 as a gas. And we would need to combine those to make water. To show an example here, I'm going to show an example for methane. So the reaction that would happen for the enthalpy of formation, or the standard heat of formation for methane, we're going to make exactly 1 mole of CH4, and we're going to make it from the elements in what we call their standard states. For carbon, that's a solid. For hydrogen, it's H2 as a gas. So balancing everything to make exactly 1 mole of product, we'll have carbon plus 2H2 makes CH4. Right? And the physical states here actually do matter as we're listing them. And so then delta HF naught for this process is negative 74.8 kilojoules. What that means is when we do this reaction to make methane from its elements, starting elements in their standard states, that process releases energy, which means it's probably reasonably favorable to happen as long as there's not some other factor called entropy that causes some problems, which is a topic that we get into, a lot more in 1212. Now, a couple last things about standard heats of formation before I show how do we use them to find delta H of an entire reaction. Enthalpies of formation for elements in their standard states are 0. So the enthalpy of formation for just plain H2 in the gas phase is 0. But the enthalpy of formation for hydrogen as like a liquid or just hydrogen as a plain atom instead of H2 is not 0. So it has to be for that element in its particular standard state. Now, using enthalpies of formation to find delta H for a whole reaction, this delta H here is the delta H of our whole reaction. Probably should have a reaction subscript here, and I'll show that actually in the next slide when we do our examples. It's going to be, and this really should be like, it's going to be the sum of all the enthalpies of formation of all of our products minus the sum of all the enthalpies of formation of all of our reactants. Right? I'm going to show how exactly that process works in a second. This is kind of a somewhat of a notation that kind of shows it, but stoichiometry here does matter. So whatever your coefficient for something is in a balanced reaction, you're going to take the enthalpy of formation of that compound, like for A as a reactant. We're going to take its enthalpy of formation and we're going to multiply it times whatever that coefficient is. So stoichiometry does matter to this calculation. And I think the easiest thing here is to just show an actual full example. And that will make all of this kind of setup make a lot more sense. But the biggest thing here, enthalpy of change of enthalpy for a reaction, it's the enthalpy of formation for all the products minus the enthalpies of formation of all the reactants. So to show, working through an example of this, we want to calculate delta H of our reaction for this reaction that we're given. N2H4 as a liquid plus N2O4 as a gas, going to N2O as a gas plus 2H2O as a gas. And so to go through and work this problem, get kind of some clear whiteboard space here to set it up. To show this, our delta H for the whole reaction is going to be really the sum of all of our enthalpies of formations for our products minus that same sum for all of our reactants. Now, to put all of the pieces in so we see how this works, we'll start with the product side of things. So our products are N2O and H2O. So for N2O, come down here, its enthalpy formation is positive 81.6 kilojoules per mole. So we're going to have 2, right, because we have 2 N2Os in our balanced reaction, times 81.6 kilojoules per mole, plus, because we're taking the sum for all of our products, right, so the sum for all of our products, our other product is H2O, its enthalpy of formation is negative 241.8. It also has 2 moles in the balanced reaction, so we'll have 2 times a negative 241.8 kilojoules per mole. There's our sum for all of the products. And now we're going to subtract, I'm going to show this on the line below, minus all of the same thing for our reactants. Sorry, I couldn't fit all of it going across in one line. And so subtracting for our reactants part, doing the same thing. For each of these, there's only one of them. So for N2H4, it's going to be 1 for its coefficient times the enthalpy of formation of the N2H4, which is positive 50.6 kilojoules per mole, plus, right, so we get the sum of all of our reactants. N2O4, we have 1 of them, so 1 times its enthalpy of formation for N2O4 is positive 11.1 kilojoules per mole. Now it's just a matter of actually doing all of the algebra to put all of this together. Right, so I'm going to actually calculate this here as we go. I didn't have this one done ahead of time. And so hopefully give everyone kind of a minute here to catch up on your own as well. And at the very end of this, I get negative 382.1 kilojoules per mole. Now, One last thing I do want to point out here. This was the final delta H of our reaction. The end of all of this. Sig fig wise, right? Since we are doing like a subtraction, really like we're adding and subtracting pieces here, it's really about the decimal place that we know things to. And so we kind of know most of these decimal places. Like if we're being really, really picky, maybe here when we do 2 times 81.6, we'll actually like 100 something that maybe we know to the ones. Probably most of the time you're probably safe going to the first decimal place here or the ones. Probably what will happen more often than not will be particular, like this is the number of significant digits we want. Because this is one area where significant digits can get a little bit murky because it mixes and matches like our different operation types. So just kind of something to be aware of, kind of be careful. If you're uncertain whether sig figs are going to be super important to that, maybe just ask. Everyone's going to have a little bit different kind of quiz and test policies on how those are going to work going forward. And so you may just ask your individual instructors too, as far as like if the problem doesn't specify the right number of significant digits for these types, because it is one where they can get a little bit strange. All right, so big thing here, and again, if you have me for lecture, I'll have some Chem 101 examples. If you have Dr. Herbert or Mr. Kruger, I believe they're using like Master in Chem and some other things to give you some access to some additional example problems and homework problems. These types of problems, kind of similar to Hess's law, once you do a few of them, they start getting really easy. The biggest things to just be really careful of, pay attention to sign conventions, right? So here it's products minus reactants. So products minus reactants kind of keep the order intact, but also pay attention to stoichiometry for this method. If we're using our enthalpies of formation, the stoichiometry part is also going to matter. Past that, I think that's it for this first lecture. I know it's already gone on for a good little bit longer than what I had intended, but please give me feedback on some of the things that you see in this that are good, bad, otherwise, so I can try to adjust these going forward. If you can't hear things clearly or if the closed captioning suck or something of that sort, let me know, and I will try to do my best to kind of adapt things and make things better for future videos for everybody. But hopefully, like I said, this method works. We're gonna have to make do with what we can to try and kind of present all this information. And if you do have questions, please be in contact by email. We'll have some different like potential video conferencing for meetings potentially as well as we get going here in the semester, picking back up. Just be in touch, and we will do everything we can to kind of try and help out. Expect probably pretty shortly you can have another video as well on the start of Chapter 6. Those will be kind of our starting materials for this week. And like I said, if you have questions, please ask. Otherwise, we'll see you next time.